This is Chapter 10, Quality Control. So here's the phases of quality assurance. So the least progressive is on the left. So this is acceptance sampling. So you have inspections of lots before or after production. And then the next one is in the middle is process control. This is where you have inspection and corrective action during production. And then the most progressive is on the right, and this is where you have quality built into the process. So here's a question: how much do you inspect? So on the left, if you look at this red line, this is the cost of passing defects. So this is really that cost, the external cost to the customer. It's either if you're inspecting at the tail end, this is the cost of giving the customer something bad. And then this is the cost of inspection. So the more you inspect, the less likely you are to give the customer something bad. And then this is the cost of passing on defects. So if you add those two together, you get this other curve. So that curve, that dashed line curve, is the sum of those two. And if you look right here, this is the point when this top curve is the lowest. So it's actually where these two cross. And that's the optimal. So in this case, you're spending the same for inspection as you're spending for inspection. So you're spending the same for inspection versus the cost of passing on defects. So that's sort of the optimal point. So where to inspect in the process? So here's some typical inspection points. The first is at the very beginning. Raw materials are your purchased parts, so it's sort of your incoming inspection. The second most obvious is just before when you finish the product. The next one is before a costly operation. So if you're gonna put something together and it costs you a whole bunch of labor to put it together, you might want to inspect just before you put it together, make sure it's good, rather than afterwards. And then before an irreversible process. So we build boards that are for flight, and just before you do the flight, before you one of the last steps is you put a coating over the board that cannot be replaced. It protects the board, it seals the board. So before we put that coating on, you test the board, make sure it works. And then the last thing you do is you put the coating on, and then you retest the board. So actually before a covering process, so it's that covering is sort of irreversible. But you could say, well, we're putting a bunch of cards in a box. Before I put the screws on the box and cover it up, I want to test it. So you might do that. So those are examples of places to inspect in the process. So centralized versus on-site inspection. So it really affects the cost and the level of distribution. So the benefits of or the times you want centralized inspection is when you have specialized tests that must be completed in a lab, where you have more specialized testing equipment, or a more favorable testing environment. On site is you really have quicker decisions. So this is where you know right away that something's wrong. You avoid the introduction of extraneous factors. So an extraneous factor may be it works great, but then when we ship it, it bounces down the road and then it gets broken. Well, that's an extraneous factor driving down the road. Quality at the source. So if you want quality at the source, you need to have some kind of inspection at the source. So this is a control chart, and we talked about this, we touched on it in chapter 4 when we were going through the process improvement tools. But this is where you have sort of the middle, and you have the upper control limit. So this line here is the upper control limit. This line is the lower control limit. This is the one right in the middle, the mean, the average. And this is normal variation due to chance. And then this piece here, that's out of control. So this is abnormal variation due to assignable sources. And so on both sides of this is assignable sources. So each point in this chart represents a sample of n observations. So it might be a sample of 1 observation. It may be a sample of 100 observations, depending on how you're controlling it. You might sample everything, or you may do, and we'll talk more about lot sampling later on. So errors, there's 2 types of errors. One is a type 1 error. So a type 1 error is you're concluding the process is out of control when it actually is. So you can also think of this as the probability of rejecting the null hypothesis when the null hypothesis is true. And sometimes you look at this as manufacturer's risk. The second is type 2 error. So this is when you conclude a process is in control when it is not. So this is the probability of failing to reject the null hypothesis when the null hypothesis is false. There's another tongue twister that I have a hard time with. And this is the customer's risk. And we'll talk more about this in the manufacturer's risk or the customer's risk. But the concept is, if you think it's broken when it's not, that's the manufacturer's risk. When you think it's good when it's broken, that's the customer's risk. So you can also look at this as the type 1 error is that little space out here on each side. So you have observations from the sample distribution, and they're going along, and so you have a normal distribution here. And now there's a couple of things that can happen. So one of them is, see this where you're going along here and it slowly goes out. Here's where the sampling distribution, you see how the sample distribution is wandering up. So so in this case, this chart does not, so there's the X bar chart and the R bar chart. So, the R chart. So the X chart reveals this shift, but in this case, the R chart does not reveal the shift. So now let's go to another one, which shows the sampling distribution here. the distribution is getting wider and wider. So here, the X bar does not show this because it still says it's okay. But the R chart, you see that as you're going along, the R chart here suddenly goes out. So here, this shows the mean charts and the range charts. The mean is the X bar, the range is the R chart. Those two charts, they have different uses, and what you want to do is you really want to be measuring both of them so you know whether your mean is going off or whether your distribution is getting wider. So managerial considerations. So one of them is at what points in the process to use control charts, what size samples to take, the sample frequency, the type of control chart to use, your variables and your attributes. So here's some non-random patterns. So the top one, this one here, you see how this is? This is a trend. We actually talked about a trend in forecasting, but it also applies to control charts. So here you have a trend where it's going in one direction. The next is a cycle. See how this is sort of looks like almost a cycle where it's going up and down. A bias. So in this case, you have too many observations on the bottom end. See how it's sort of just right. It's all on this side. So here you have a bias. And then here's one where it's like you have too much dispersion, where there's a whole bunch up here, a whole bunch down here, but not very much in the middle. So they're too spread out. So now let's talk about process capability. So here you have the process variability exceeds specification. So here's your lower specification, your upper specification, and here all of these are bad. So that's too much. And then here you have your lower specification, your upper specification, and this is probably where it sort of matches. So you got a few that are rejected here, a few that are rejected here. So this is pretty good. And then here your specification is less than the specification width. So here your specification is way down here or way up here, and your process is way in the middle. So we'll talk about this. There's times you want to do that, but this is sort of your variability is less than the specification width. So how do you improve your process capability? So one of the ways is simplify. So if you make it, some people call it, mistake proof is, so you simplify. Some people call it idiot proof, but you just make it simpler. So it's easier for people to not make mistakes. The second is standardize. Everybody doing it the same way. It allows you to train people faster. It also reduces errors because it's real easy to see. This is how you do it. Mistake proof, we also call that idiot proof. But the idea is you make it so that it can't break even if you do it wrong. The next is upgrade equipment. So if you have poor quality equipment, or your equipment is putting out poor quality products, if you just make it better, you could have better equipment. And then the next one is to automate. So the nice thing about machines is it keeps doing the same thing over and over and over, where a human could introduce an error, once you get the machine right, uh, you know, so machines aren't smart, but they're repetitious. You know, so you could get 100 bad items out of a machine, but but once you get it right, you'll get 100 good items out. So this is something called the Taguchi loss function. So this is the traditional way of doing things, where you have the lower spec and the upper spec. And what you say is, if it's inside a spec, you pay for it, and if it's outside of spec, its cost is high. It's no good. The Taguchi loss function is if we try to get everything in the middle. So this way, it costs you a little bit here, a little bit more, a little bit more. So what this does is it drives, you could think of like if you have a ball in the middle of here, it's going to just roll down to the middle and it's going to settle at this target. If there's a ball here, it's going to roll back and forth between these two limits. So the Taguchi loss function says if we measure the cost as a curve rather than the step function, you end up being closer to the target. So your operation strategy, the primary consideration for nearly all customer is achieving and maintaining quality standards is of strategic importance to all businesses. So you have product and service design, and you have increased capability to move from extensive use of control charts and inspection charts to achieve desired quality outcomes. This is the supplement to Chapter 10, which is acceptance sampling. So the acceptance sampling, the purpose of acceptance sampling is to decide whether a lot satisfies predetermined standards. So lots that satisfy these standards are passed or accepted. So there's a couple of things you can do with lots that are rejected. You can subject it to 100% inspection. In the case of purchased goods, you could return it for credit or replacement. So acceptance sampling is most useful when one of the following conditions exist. A large number of items must be processed in a short time. The cost or consequence of passing defects is low. Destruction testing is required. And then fatigue or boredom caused by inspecting large numbers of items leads to inspection errors. So sampling plans. So there's several ways you can do it. One is called a single sampling plan. So one random sample is drawn from each lot. Every item in the sample is inspected and classified as good or defective. If a sample contains more than a specified number of defects, the lot is rejected. So then the next one is a double sampling plan, and this allows the opportunity to take a second sample if the results of the initial sample are inconclusive. And then a multiple sampling plan is similar to the double sampling plan, except more than 2 samples may be required. A sampling plan may specify each sample size and 2 limits for each sample. So here's the operating characteristic curve. So here's an important characteristic of how you discriminate between high and low quality. So here here is the number this is the ideal number of samples you would have with this lot. And in this case, if you look here, the curve comes down like this. So in this case, it's very discriminating. In this case, it's not very discriminating. You're not really at the knee of the curve there. That's sort of the operating characteristic curve. So 100% inspection. So this, you theoretically discriminate between good and bad. So, but 100% inspection a lot of times is impractical, either because it's costly and time consuming or for destructive testing. So destructive testing, let me give you an example. Let's say you're buying a case of bullets and you say, well, I want to know whether these bullets are good or not. Well, you could shoot the entire case of bullets, and when you're done, you know that the entire case was good, except you have no bullets that are good. So that's a good example of destructive testing. When you shoot a bullet, it's gone, right? But you might say, okay, I'm going to shoot 2 bullets out of this case of 1,000. If they both go, cool. Risk. So now we're going, there's customer's risk, which is beta, and manufacturer's risk, which is alpha. And this, you go back to when we were talking about type 1 error versus type 2 error. So the customer's risk is the probability that a lot containing defects will be accepted. And then the manufacturer's risk is the probability that a lot containing acceptable quality will be rejected. So many sampling plans are developed to have the producer's risk about 5% and the customer's risk about 10%. So a lot of times this lot acceptance criteria is negotiated as part of the contract. So you decide up front how are we going to sample this lot, and you decide how much risk is going to go on the producer and how much risk is on the customer, and you decide. So you could it could be part of the contract, or you just say, the manufacturer may say, I'm just selling this as is. These are defects. It's your risk. Then it's your problem to go do your sampling of the lot. So the average quality of inspected lots. So an interesting feature of acceptance sampling is the level of inspection automatically adjusts the quality of lots being inspected. So that assumes that rejected lots are subject to 100% inspection. So good lots have a high probability of being accepted, and bad lots have a low probability of being accepted. So if lots are inspected are mostly good, few will end up going through 100% inspection. The poorer quality lots, the greater number of lots that come under close scrutiny. So, so if you're getting good quality stuff, it's not getting very much 100% inspection. Or if you're getting poor quality stuff, all the lots end up getting 100% inspection.